There are two reasons that we like linear programming as an optimization tool. One, we have robust algorithms for solving large linear programs. Simplex algorithm does wonders when we try to solve large linear programs in practice. Simplex algorithm is an enormously effective algorithm in practice. And the second reason that we like linear programming as an optimization tool is that we have very good optimization software for solving linear programs. By using modern linear programming solver these days, we can solve linear programs with hundreds of thousands of decision variables, hundreds of thousands of constraints on our laptops in a matter of minutes. So the modern linear programming solver available today is extremely good. Today, we're going to talk about one good linear programming solver that's available to us. And that linear programming solver is called Gurobi. So we're going to talk about the linear programming solver, Gurobi. And there are two ways for using Gurobi. The first way of using Gurobi is using Gurobi as a standalone linear programming solver. And what I mean by standalone linear programming solver is that we can write our linear program in a text file, and then we can read that text file within Gurobi, and then solve the linear program that is included in our text file, and then look at the solution, look at the optimal solution. Okay, so that's one way of using Gurobi, and that's using Gurobi as a standalone linear programming solver. Another way of using Gurobi is that we can call Gurobi within a programming language like Python, Java, C#, whatever you're comfortable with. So we can call Gurobi from a programming language. And the advantage of being able to use Gurobi from a programming language is that, let's imagine that you're writing some kind of an app in Python for a user to solve a shortest path problem. So in Python, you create all the user interfaces. You show the user the map over which you're going to solve the shortest path problem. You create all these user interfaces that's going to allow the user to click on the origin location and click on the destination location on the map. And then once the user picks the origin and the destination location, without getting out of Python, we can create a linear program that is going to solve the shortest path problem from the origin location to the destination location. Call Gurobi again within Python without getting out of Python to solve that linear program. Within Python, get the optimal solution to that linear program. And then we can display the solution to our user on the map, again, without getting out of Python. We can do all of these things without getting out of Python. Okay, so that's the second way of using Gurobi, calling Gurobi from a programming language. So today we're going to see both uses of Gurobi, using Gurobi as a standalone linear programming solver, and calling Gurobi from a programming language. And we're going to call Gurobi within Python. We're going to use Python today. Good, great. So now let's start working with Gurobi. The first thing I'm going to show you is how to put Gurobi on our computers. Let me bring up a browser. So Gurobi's website is available at gurobi.com. And then once you go to gurobi.com, you can go to Downloads and Licenses. And then in Downloads and Licenses, we go to Download Center. The piece of software that we need is Gurobi Optimizer. You click on Gurobi Optimizer and download the appropriate version for your computer, whether you're using a Mac operating system or Windows operating system or Unix, whatever you're comfortable with. So that puts Gurobi Optimizer and all the API that's necessary to connect Gurobi with Python. So that puts everything that you need. So after we download Gurobi Optimizer on our computers, the next thing we do is we go and get the appropriate license for us. In order to get the appropriate license for us, let's go back to gurobi.com again. We create an account. Once we create an account and log into our accounts, let me show you what your account should look like. Once you go to create an account and log into your account, you're going to be in your user portal. In your user portal, you go to licenses, and then you say request. When you go to request, there are different types of licenses that you can request. For academic users, one license that works well is named user academic, which works on a single machine for a single user. You can get that license. If you don't have an academic affiliation, you can go to commercial licenses. You can get either a free trial for 30 days, or you can sign up for the Gurobi's online course. In that case, Gurobi would give you a version of Gurobi software that allows you to solve linear programs with 2,000 decision variables and 2,000 constraints. And it's usually more than enough to understand how Gurobi works. So that's another way. If you're going to get an academic license for Gurobi, make sure that you're connected to the internet. Make sure that you're connected to the internet at an academic institution. So Gurobi checks that you're connected from an academic institution's network. Otherwise, you will not be able to get an academic license. So that's how we put Gurobi on our computers. Okay. So now once we put Gurobi on our computers, let's learn how we can use Gurobi as a standalone linear programming solver, and let's also learn how we can call Gurobi within a programming language. Okay. In order to be able to do that, we're going to have a running example. Here's what our running example is going to look like in this lecture. We're going to have a running example for using Gurobi as a standalone linear programming solver. Here's what our running example is going to look like. We're selling cloud computing services to two classes of customers, memory-intensive customers and storage-intensive customers. Each memory-intensive customer uses 100 gigabytes of RAM and 200 gigabytes of disk space. Each storage-intensive customer uses 40 gigabytes of RAM and 400 gigabytes of disk space. A yearly contract with a memory-intensive customer brings $2,400. A yearly contract with a storage-intensive customer brings $3,200. At our disposal, we have 10,000 gigabytes of RAM and 60,000 gigabytes of disk space. And for whatever the reason is, we don't want to sign contracts, let's say, with more than 140 storage-intensive customers. We want to figure out how many contracts we should be signing with memory-intensive customers and how many contracts we should be signing with storage-intensive customers so that we maximize the yearly revenue while making sure that we do not overuse the amount of RAM and the storage space that we have available, and also while making sure that we do not sign more than 140 contracts with storage-intensive customers. Let's try to formulate this problem as a linear program, and then let's try to solve that linear program by using Gurobi as a standalone linear programming solver. Here. As our decision variables, we're going to have two decision variables, number of contracts that we sign with memory-intensive customers and number of contracts that we sign with storage-intensive customers. So let's say our first decision variable is going to be xm, number of memory-intensive contracts that we sign, number of memory-intensive contracts signed. And our second decision variable, let's denote that by xs, that is going to be the number of storage-intensive contracts that we sign. Good. Let's write a linear program that's going to maximize the yearly revenue while making sure that we do not overuse the amount of RAM and the disk space that we have. We're maximizing the yearly revenue. Each contract with a memory-intensive customer brings $2,400. And we're signing contracts with XM memory-intensive customers. So this is the revenue that we collect from the memory-intensive customers. And each yearly contract with a storage-intensive customer brings $3,200. And we're signing contracts with excess storage-intensive customers. So this is the revenue that we collect from the storage-intensive customers. This is the total yearly revenue that we collect, which is what we're trying to maximize. Let's write a constraint on the amount of RAM that we have available. Just a little bit more, okay. Each memory-intensive customer uses 100 gigabytes RAM. Each storage-intensive customer uses 40 gigabytes of RAM. These are the number of memory-intensive customers that we sign. Each one of them uses 100 gigabytes of RAM. And these are the number of contracts that we sign with storage-intensive customers. Each one of them uses 40 gigabytes of RAM. So that is the amount of RAM usage that we have. And the total amount of RAM that we have available is 10,000 gigabytes. So we make sure that we do not overuse the amount of RAM that we have available. Likewise, let's write a constraint on the amount of disk space that we have available. These are the number of memory-intensive contracts that we sign. Each one of those contracts uses 200 gigabytes of disk space. And these are the number of storage-intensive contracts we sign, and each one of those contracts uses 400 gigabytes of disk space. That is the total amount of disk space that we use. That should be no larger than the 60 gigabytes of disk space that we have available. That should be no larger than the 60,000 gigabytes of disk space that we have available. Okay. And we said at the beginning that we're not going to sign more than 140 contracts with storage-intensive customers. So excess variable is going to be at most 140, and our decision variables are non-negative. So this is the linear program that we would like to solve. Maximize real revenue subject to RAM constraint, storage constraint, and we don't want to sign contracts with more than 140 storage-intensive customers. Okay, let's solve this linear program by using Gurobi as a standalone linear programming solver. Let me write this linear program in a simple text file. And the format that we're going to use for this text file is going to be more or less exactly what we wrote in our mathematical notation. Okay, so the format we're going to use for this text file is going to be more or less what we use in our mathematical notation. I want to maximize my objective function. Good. What is my objective function? 2400xf plus 3200xs. That's the objective function that we would like to maximize. And Gurobi doesn't care about white space, so I'm just going to put a tab in there so that our linear programming text file looks a little bit more pleasant to the eye. Next, we're going to write the constraints. When we start writing the constraints, we open a new section by writing subject to. Now we're going to write down our constraints in more or less the same format that we use in our mathematical notation. Our first constraint is 100xm plus 40xs is less than or equal to 10,000. 100xm plus 40xs is less than or equal to 10,000. That's our first constraint. That's our second constraint. 200xm plus 400xs is less than or equal to 60,000. Okay. The third constraint that we have is a very simple upper bound constraint on the decision variable xs. The third constraint we have is a simple upper bound constraint on the decision variable xs. We could write that constraint by putting xs is less than or equal to 140 under our constraints. But since our third constraint is a very simple upper bound constraint on the decision variable xs, it's better to write those simple upper bound constraints in a separate section called bounds. These are simple upper bound constraints on our decision variables. And the reason it's better to write these simple upper bound constraints in a different section is that Gurobi solver treats these upper bound constraints declared in the bound section in a much more efficient manner. Okay, so if you get a very simple upper bound constraint on your decision variables, it's better to specify those upper bound constraints in this special section called bounds rather than writing them underneath the subject to section. In this way, Gurobi treats those upper bound constraints in a more efficient manner. Good. And by convention, any decision variable, unless we say upper bound, unless we say non-negative, any decision variable, unless we say otherwise, any decision variable, unless we say otherwise. By convention, any decision variable, unless we say otherwise, is treated as a non-negative decision variable by Gurobi. So we do not need to specify that our decision variables are non-negative, because again, unless we say otherwise, any decision variable is treated as a non-negative decision variable by Gurobi. So this is the whole specification of our linear program. Like I say, we don't need to specify the non-negativity constraints on our decision variables. Gurobi by default treats the decision variables as non-negative. So then to finish the specification of our linear programming file, to finish the specification of our linear programming file, we put and. This is all there is to it. Okay. So then the format we have here and the format we have in the text file here, they are very much similar. Okay. Maximize the objective function, subject to the constraints, and we have a simple upper bound on decision variable xs. Unless we say otherwise, all the decision variables are treated as non-negative by Gurobi, so I do not have to write something special for my non-negative decision variables. Good. So let's save this text file, and I'm going to save this text file on my desktop, and let's call this text file as cloud.lp. It's important to give it LP extension because the format over here we used is called the linear programming format. So by putting the LP extension in our file name, we're going to be able to tell Gurobi that this file is in the LP format. There's a few other formats that Gurobi can use, but we're not going to talk about those other formats. LP is the simplest and most intuitive format. Okay, so let's save our text file on the desktop by using LP extension. Our text file's name is cloud.lp. Save. Good. Let me bring a terminal window. Okay. Our text file was included under the desktop, so let me go to the desktop. Okay. Let's make sure that cloud file is over there. So indeed, the cloud file is over there. So now let's open the Gurobi software. Gurobi.sh brings up the Gurobi software as a standalone solver. There we are. So the first thing we're going to do is we're going to read this linear program included in this text file. And the way we read the linear program is the read command, read cloud.lp. So read cloud.lp reads the linear program that is included in the text file, cloud.lp. And after it reads the linear program included in the text file, it returns a model that includes that linear program. So now let me take a variable, let's call that variable my model, and set that equal to this linear program that Gurobi just read. Okay, so when I said read some file name, Gurobi reads the linear program included in the text file and returns a reference to that linear program. So now this variable my model is pointing a reference to the linear program that we just read. Now let's read our linear program. So we now read that linear program, and as we read it, Gurobi is printing some information. Our linear program has two rows, meaning that it's got two constraints. It's got two columns, meaning that it's got two decision variables, and four non-zeros, meaning that there are four non-zero values in the constraint matrix. Okay. Good. So as we go along, we're learning some comments. So let's make a note of the comments that we're learning. We're not going to look at this text file anymore. That includes our linear program. I'm going to minimize that. Let me put the shell over on the right-hand side. Good. So now what did we learn? We learned the read command in Gurobi. And that reads a linear program from a text file. And after we read a linear program, we created this variable in Gurobi called myModel. It's now pointing to the linear program that we just read. So now we have a variable called myModel in our Gurobi environment, and this variable myModel is pointing to the linear program that we just read. Good. So now we know how to read a linear program. After we read a linear program, the next thing to think about is solving the linear program. The way we solve a linear program is get our linear programming model, myModel, dot optimize. This is going to solve a linear programming model. So now we learned another Gurobi command. So if I take a Gurobi model and say optimize, this solves a linear programming model. So let's solve the linear programming model that we just read. Okay, good. So now Gurobi cranks up the linear programming solver or whatever algorithm it's using. It runs the iterations of the simplex method, and then it terminates with the optimal objective value of the linear program that we solved. So the optimal objective value of this linear program is evidently 5.2 times 10 to the 5. 5.2 times 10 to the 5 is the optimal objective value of this linear program. And before Gurobi starts solving the linear program, it prints some information about the linear program. Matrix range, objective range, bounds range, and right-hand side range. Matrix range is the smallest and the largest values of the coefficients of the constraints. So the smallest is 140, largest is 400. Those are those values. Objective range are the smallest and the largest values of the entries in the objective function coefficient, 2400, 3200. It's giving us rough cut estimates of those numbers. Bounds range is the smallest and the largest values of the bounds on our decision variables. We have only one bound, it's 140. There is that, so it's roughly on the order of 100. And right-hand side is the range is the smallest and largest values of the right-hand side, 10,000, 60,000. There are those values. Okay, good. And again, we solved this linear program. The optimal objective value came out to be 5.2 times 10 to the 5. After we solve a linear program, a natural thing to do is look at the optimal solution to the linear program. And one way to look at the optimal solution to a linear program is to take my model and then print an attribute of this model. And then we're going to print the X attribute of this model. The X attribute of the model corresponds to the values of the decision variables. So now we learned a new command here. Gurobi model dot print attribute. And then as an argument to that function, we give the X. So that's going to print the values of the decision variables in the optimal solution. Let's do that. Let's see what we get. So value of the decision variable X in the optimal solution is 50. Value of the decision variable X in the optimal solution is 125. So this is one way to query the optimal solution to a linear program. What else? From this point on, we can interact with Gurobi almost like we're interacting with a piece of Python code. Like, for example, if you get a Gurobi model and say get vars, Gurobi returns an array that includes all the decision variables in our model. So if I say my model.get vars, this returns an array that includes all the decision variables in our model. And let me take a variable called myvars and assign it to the array of all the decision variables in our model. Okay. So if I take a Gurobi model, say get vars, this is going to return an array that includes all the decision variables in our model. So now this variable myvars is pointing to an array that includes all the decision variables in our model. So then we learned something new. So if I take a Gurobi model and then say dot get vars, it returns an array that includes all the decision variables in our model. So now I have this variable myvars, which is an array that includes all decision variables in our models. Good. So now let me print that my vars array, just like I would do in Python. That prints an array that has two entries in it. Both entries are Gurobi variables. The first entry is the variable xm, currently value at 5. The second entry is the variable xs, currently at value 125. Correct. So now I have this myvars array that includes all the decision variables in my model. Again, I can interact with that array just like I'm interacting with any other Python array. Like, for example, print myvar0. This would, if I say myvar0, that would be pointing to the first element of that array. That would be pointing to the first decision variable in my model. And each Gurobi variable has two fields, a name field and a value field. So if I have a Gurobi variable, and I say dot var name, I'll be pointing to the variable name for that Gurobi variable. And if I have a Gurobi variable, again, let's point to the first element of that myvars array. That's the first decision variable in our model. If I point it to the x field of that variable, that will be the value of that decision variable. So now once you say print myvars 010.3.var name and myvar 010.3.x, this would print the name of the first decision variable in our model, and this would print the value of the first decision variable in our model. Let's see. Indeed, the name of the first decision variable in our model is x1, and the value of the first decision variable in our model is 50. Okay. So then we learned two things. Each Gurobi variable has two fields, var name and x. So a Gurobi variable has two fields, a var name field and an x field. And you can query those to get the values of the decision variables. Good. What else? We can also query the constraints. So if I say my model dot get constraints, this would return an array that includes all the constraints in our model. If I say my model dot constraints, this would return an array that includes all the constraints in our model. So let's do that. So now my model that get constraints, it returns an array that includes all the constraints in our model. And let me get a variable called myconst. So that's going to keep track of the, let's see, is it consistent my constraints? That's going to keep track of an array that includes all the decision variables in our, all the constraints in our model. So let's say Gurobi model dot get consts. That returns an array that includes all the constraints in our model. So now I have another variable in my Gurobi environment that's called myconsts. Okay, so now again we can print that variable. That's not going to be terribly informative. Say, hey, I have a constraint R0 and another constraint R1. This is the first row, this is the second row of my constraints. So that's not terribly informative. Lastly, we haven't seen this yet, but in a few lectures, we're going to start talking about the duality theory. In duality theory, we're going to see that once we solve a linear program, associated with each constraint, we're going to have a dual variable. So now we're going to see that in a few lectures. So when we cover duality theory in a few lectures, we're going to see that once we solve a linear program, associated with each constraint in our linear program, we're going to have an optimal value of the dual variable associated with each constraint. So we can also query the optimal values of the dual variables associated with each constraint. We don't know what that means yet. We're going to see it in a few lectures, but let me just show you how we can query the optimal value of the dual variable associated with each constraint in our linear program. So what we can do is the following. Associated with each constraint in Gurobi, Gurobi, we have two fields, which is the name of the constraint and the dual variable of the constraint. So now let's do something like this: print my constraint zeroth array, zeroth element. So this is the first constraint in our model. Dot constraint name. This will return the name of that constraint and print my constraints zeroth element dot pi this way. That will return the optimal value of the dual variable associated with the first constraint. Okay, dot pi returns the value of the dual variable associated with one of the constraints. So let's write down what we wrote. Let's write down what we wrote. Each Gurobi constraint, this is the zeroth entry of my constraints array. So each Gurobi constraint has two fields, constraint name and pi. The Gurobi constraint has two fields. The first one is a constraint name. And the second one is pi. Good. Let's see that. So the first constraint is named R0 by default, and the value of the dual variable for that constraint is 10. Great. And lastly, if you want to get the values of the dual variables associated with each constraint, there's a simple way to do it. We say go to a Gurobi variable my model, and we say print attribute. But now the attribute that we're printing is the pi attribute. Okay, so it gives us a list of all the constraints and the dual values of the dual variables associated with each one of these constraints. So now let's write that thing that we learned. We can go to a Gurobi model and say print attribute and say pi. They will return the values of the dual variables associated with each one of the constraints. Good. So this was about using Gurobi as a standalone linear programming solver. We write the linear program that we want to solve in a text file, read that text file within Gurobi, solve the linear program, including that text file, and then look at the optimal solution. The next thing we're going to talk about is how we can write a Python code, write a piece of Python code that is going to create, solve, and look at the optimal solution to that linear program, all within Python, all calling Gurobi within Python without getting out of Python at all. Okay, so next thing we're going to do is we're going to write a piece of Python code that is going to create, solve, and look at the optimal solution to a linear program by calling Gurobi within Python without getting out of Python. Okay, good. So we're going to write a Python code that is going to solve this linear program within Python. So let's record this linear program on a clean page so that, again, we're going to have that in front of us. Maximize the objective function 2400 xm plus 3200 xs subject to 100 xm plus 40 xs is less than or equal to 10,000, and 200 xm plus 400 xs is less than or equal to 60,000, and xs is less than or equal to 140. Our decision variables are non-negative. Okay. Now let's write a piece of Python code that is going to solve this linear program within Python by calling Gurobi within Python without getting out of Python at all. Let's create a new Python file, and let's call this file cloud example. Good. First thing we're going to do is let's import the Gurobi packages. Good. The next thing we're going to do is we're going to create an empty linear program, and this function model creates an empty linear program. And we can give a name to our linear program also. It's not terribly important, but let's give a name to our linear program. Let's call our linear program plot example. So this function model creates an empty linear program and returns a reference to that empty linear program. So let's use the Python variable my model to refer to this empty linear program that we created. So now what we did here is we create an empty linear program, and this Python variable my model is now pointing to that empty linear program that we just created. So now we learned something here. Model creates an empty linear program. Now I have a Python variable my model pointing to an empty linear program. So let's record those. So this function model creates an empty linear program. Now I have this Python variable called my model pointing to an empty linear program. Good. Next thing we're going to do is we're going to add decision variables into our linear program. I have two decision variables, xm and xs. Let's create and add these decision variables into our linear program. So if I go to my model and say add var, this adds the decision variable into the linear program. Okay. If we go to our linear program, my model, and say add var, this adds the decision variable into our linear program. Let's add our first decision variable. So the type of this decision variable is continuous. In a linear program, our decision variables can take continuous values, fractional values. So the type of our decision variable is continuous. Let's also give a name to our decision variable. So I'm creating a decision variable for the decision variable xm. The text name of that decision variable is xm. So then when we say my model.add var, it adds a new variable into the linear programming model and returns a reference to the variable that we just added. So now let's take a Python variable. Let's take a Python variable called xm. And let's use that variable xm. Let's use that Python variable xm to point to this decision variable that we just created. Okay. So now we learned something. If you go to a Gurobi model, say add var, it adds a new decision variable into our model and returns a reference to the variable that we just added. So if I go to a Gurobi model and say add var, we add a new decision variable into our model and return a reference to that variable, to that decision variable that we added. So now the Python variable xm is pointing to the new decision variable that we just added. Similarly, let's add a decision variable for our second decision variable corresponding to xs. xs, my model.add var, type of this decision variable is, and the name of this decision variable is xs. The text name of this decision variable is xs. So now we have two Python variables, xm and xs, pointing to the decision variables that we just constructed. And the second decision variable xs has a simple upper bound on it. The second decision variable xs has a simple upper bound on it, upper bound of 140. So when we're creating a decision variable, we can actually quickly specify those upper bounds by saying ub equals 140. So the second decision variable that we constructed, its text name is xs, has an upper bound on it and set upper bound of 140. Okay. After we construct our decision variables, the next thing that we need to do is call this function called update. What that function does is it makes sure that the decision variables that we constructed are properly registered into our linear programming model. Okay. So after we create our decision variables, we have to call this function called update that makes sure that the decision variables that we constructed are properly registered into our Gurobi model. So then we learn something new. Gurobi model.update properly registers the decision variables into our linear programming model. The next thing we're going to do is we're going to construct and add the objective function into our model. We're going to construct and add the objective function into our model. What is our objective function? 200xm plus 3200xs. In order to do that, we're going to construct an empty linear function. And the way we construct an empty linear function in Gurobi is linexpr. This creates an empty linear function. So we learned something new. Linexpr. Linexpr creates an empty linear function. So let's say the Python variable objective expr is now pointing to that empty linear function. So now I have a new Python variable objective expr over here. We're going to fill that empty linear function with 200 times the first decision variable, 3200 times the second decision variable. Objective expr add 2400 times the first decision variable, and also keep on adding 3200 times the second decision variable. So now we created the linear function that includes our objective function. We constructed a linear function that includes our objective function. So now we're going to go to our model, set the objective of our model, as this linear function that we created. And we also want to make sure that we maximize this function as opposed to minimizing. That is facilitated by grb.maximize. So now my model is an objective function, which is given by this linear expression that we created and filled it. Okay. We learned something new. This is how we create an empty linear function, linear XPR. And also, if you go to a Gurobi model and set objective, that sets the objective. Dot set objective. Gurobi model dot set objective sets the objective function of a linear programming model. What's next? We're going to now create our constraints, the first constraint and the second constraint. When we create our constraint, the first thing we're going to do is we're going to create a linear function that includes the left-hand side of the constraint. Okay, so let's add the first constraint. We're going to create an empty linear function that includes the left-hand side of the first constraint. Let's do that. Let's create an empty linear function. Let's call that first constraint expression. Let's create an empty linear expression. Okay. And then into this linear expression, let's add 400 times the first decision variable, 40 times the second decision variable. First constraint expression, we're going to add 100 times the first decision variable. This XM I'm referring here is this Python variable XM. This XM that we're referring here is the Python variable XM. And also into the first constraint expression, let's also add 40 times XS. This XS we're referring here, and here are the Python variable XS. So now we created a linear expression that keeps track of the left-hand side of the first constraint. Let's add the first constraint into our model now. My model dot add constraint. Okay. Left-hand side of the constraint, the left-hand side of the constraint is this linear expression, is this linear function that we constructed. Okay. What is the sign of this constraint? It's a less than or equal to sign. And the right-hand side of this constraint is 10,000. The sign of that constraint, which is specified by the sense parameter, Gurobi dot less than or equal to, and the right-hand side of the constraint is 10,000. And we can also give a name to our constraint. Let's give a name to our constraint. Let's call that constraint as this was the ramp constraint. So that's our ramp constraint. Now we added the first constraint into our model. Again, what was the whole idea? We created an empty linear function that keeps track of the left-hand side of the constraint. So now when we add a constraint, this is left-hand side. This is the sign of the constraint. This is the right-hand side. And the first constraint was ramp constraint. So we gave a name to our constraint. Good. We learned something new. We learned something new. We learned something new. Add constraint. Gurobi model dot add constraint. Good. If you're working with a more recent version of Gurobi, it may ask you to change this add constraint function to add L constraint. That's a linear constraint. It's not terribly important. If your Gurobi's version is more recent than what I have in my computer, you may need to change add to an add L constraint, a linear constraint. Again, it's the same function essentially. Let's add the second constraint to our model. The second constraint's left-hand side is 200xm plus 400xs, and the right-hand side is 60,000. So the second constraint expression, that's again another empty linear expression. Second constraint expression, we're going to add 200xm plus 400xs. Good. So now let's go to our model. Add constraint. Left-hand side is this linear function that we constructed for the second constraint. The sign of this constraint is less than or equal to. And the right-hand side of the constraint is 60,000. And this was a constraint on the amount of storage we had available. So let's call this constraint storage constraint. Good. So now we created our decision variables. We created and added our objective function. We created and added the two constraints. And we do not need to worry about the third constraint over here. Xs is less than or equal to 140, because when we were creating the decision variable xs, we specified an upper bound of 140 on that decision variable. And after we create our objective function and the constraints, we need to call this update function one more time so that the objective function and the constraints are also properly registered. You're asking yourself, when is the right time to call these update functions? At minimum, you need to call the update function twice. Once after you create your decision variables, and once after you create the objective function out of your constraints. You can call my update as often as you want, it's harmless, but the minimum number of times that you need to call the update function is twice, once after we create our decision variables, and once after we create our objective function and all the constraints. So if everything was right, we have our decision variables, objective function, all the constraints. We create the linear program that we want to solve. Let's make sure that the linear program is created in the correct form. But then what we can do is we can take our model, linear programming model, and say write and give a file name. This would dump the linear program that we create into a text file, so you can visually look at that text file to make sure that we constructed everything correctly. So let's say cloud example output. Okay. We give an extension of LP to this file just to make sure that Gurobi understands everything is going to be output in LP format. So now hopefully when we run our code, we're going to see in this directory structure cloud example output.lp that is going to include the linear program that we constructed. So let's run this piece of code. Cloud example run. Good. So now we got cloud example output.lp. Let's look at what that linear program looks like. Maximize 2400 plus 2400 XM plus 3200 XS. Here's our RAM constraint. Here's how we see the names of our constraints. 100 XM plus 400X is less than 10,000. Here's our storage constraint. 200 XM plus 400X is less than 60,000. And we have a simple upper bound on the decision variable XS. There's that. So this is exactly the linear program that I wanted to solve. So the Python code that we have constructs the linear program in the correct fashion. The next thing we're going, so then we learned another subroutine in Python that is called a Gurobi model.write. Great. So the next thing we're going to do is we're going to solve this linear program. Let's solve this linear program. And the way that we solve a linear program is my model.optimize. Great. So let's run this piece of code now. Hopefully it's going to solve this linear program. Run, what is our program? Cloud example.py. That's here it is. Run it. So Gurobi output whole bunch of stuff. Process finished with exit code 0. So it ran the simplex method on our linear program. We got an optimal objective value of 5.2 times 10 to the 5. So it seems to be solving the linear program just fine. That's great. The next thing we're going to do is after we solve the linear program, we got to look at the optimal solution possible. Good. So now we learned another subroutine. If I go to a Gurobi model, say optimize, we solve the linear program. Okay, great. The next thing we're going to do is we're going to look at the let's say the optimal objective value of our linear program. The way we look at the optimal objective value of our linear program is as follows. My model has an objective value field. And let's say we assign a variable objective value to it. And let's print that value. Good. So let's run this piece of code. Good. So then this is how we retrieve the optimal objective value of a model. My model dot, we refer to the field objective value. We indeed printed out the optimal objective value, 520,000. So we learned something else. So a Gurobi model has a field called objective value. Good. Next, let's look at the optimal values of our decision variables. Let's get the optimal values of our decision variables. Here's how we're going to do that. If I go to a Gurobi model and say get vars, if I go to a Gurobi model and say get vars, this returns an array that includes all the decision variables in our model. So let's assign that array to this Python variable called myvars. So now myvar is an array that includes all the decision variables in our model. So then we can iterate over this array. Okay. So for, let's say, my current variable is in myvars, we can print the values of these decision variables and we can print the values of our decision variables. So let's say print, look at the current variable, and let's get the name of that decision variable. And if you have a Gurobi variable, the field var name returns the name of that decision variable. Let's also get that variable and print the value of that decision variable. And if you have a Gurobi variable, the field x returns the value of that decision variable. Let's make that a string so that we don't get in trouble. So now what we wrote over here is that, we looked at our model, we got out an array that includes all the decision variables in our model. So this array myvars now is an array that includes all the decision variables in our model. So now we iterated the elements of that array. So then current variable in each iteration is going to be a Gurobi variable. So then for each one of the variable in my model, for a Gurobi variable, we can look at the field var name to get the name of that variable. And we can look at the field x for a Gurobi variable to get the value of that decision variable. So then we learned a whole bunch of stuff here. We can go to a Gurobi model, say get vars, to get an array of all the decision variables. We can go to a Gurobi model and say get vars to get an array of all the decision variables in our model. And also, if you have a Gurobi variable, we can look at the field var name to get the name of that variable. And then we can look at the field x to get the value of that variable. So then this loop that we wrote over here is going to loop over all decision variables, and it's going to print the name and the value of each one of our decision variables. Let's run this piece of code and let's see what happens. Okay, so here's the output. We looped over every decision variable, xm. Here's the name of that variable. Here's the text name of that variable with value 50. Here's the name of that variable with value 125. Okay. And when we're printing these variables, these xm, xs is the text name of these decision variables. xm and xs is the text names of these decision variables. That's what comes up. If you want, let's change the text name of these variables to x underscore xm and x underscore xs. So if I run this code again, it's printing the text name of those decision variables, if you like. Okay, great. So now I know after solving a linear program, now we know how to grab the optimal objective value, linear program dot objective value field, and also we know how to loop over all decision variables and look at the optimal values of our decision variables. Last thing we're going to do is we're going to loop all the constraints of our model, and we're going to look at the optimal values of the dual variables associated with our constraints. So if I go to my model, our linear programming model, and say get constraints, it returns an array that includes all of the constraints in our model. So let's assign that array to this Python variable, my constraints. So now let's loop over every constraint in our model. And now let's print the name of each one of these constraints. And let's print the optimal value of the dual variable associated with each one of these constraints. So each Gurobi constraint has a field in it that's called constraint name. That is the name of the constraint. And each Gurobi constraint has a field on it called pi. That is the optimal value of the dual variable associated with that constraint. And that's a number. So let's convert that number into a string. Good. So then we learned certain things here. If you go to a Gurobi model, say .get constraint, it gives us a list of all the constraints in our model. we go to a Gurobi model and say get constraints. It returns an array that includes all the constraints in our model. So now we're looping over all the constraints in our model. For each Gurobi constraint, there are two fields, constraint name and pi. Constraint name is the name of the constraint, and pi is the optimal value of the dual variable for that constraint. So if you have a Gurobi constraint, we have two fields, constraint name and pi. Good. Let's run this piece of code and see what we have. So now in our last loop, we looped over each one of the constraints in our model. We printed the name of each one of our constraints. RAM constraint was the name for our first constraint. There we go. RAM constraint was the name for our first constraint, and storage constraint was the name for our second constraint. So we print the name and the optimal value of the variable. We print the name for the second constraint and the optimal value of the second constraint of the second constraint. Optimal value of the dual variable for the second constraint. Okay, good. So this is how we can call Gurobi within Python to construct a linear program, solve a linear program, and look at the optimal solution. Okay, good. The example that we constructed in this Python code was very small. We had only two decision variables. So we created each one of these decision variables manually, one by one. And we also had only two constraints. So we had two decision variables. There we go. We had two decision variables. This linear program that we constructed had only two decision variables. We constructed these two decision variables manually, one by one. And likewise, we had only two constraints. We just constructed each one of these constraints manually, one by one. Okay, so it wasn't too bad. Good. And then after we constructed our decision variables, objective function, and the constraints, we wrote the linear program in a file just to make sure it's okay. We solved it, and we queried the optimal objective value. We queried the values and the names of the constraints. We queried the values and the names of the decision variables in the optimal solution, and we queried the names and the optimal values, the dual variables associated with each one of our constraints. Good. Okay. So in the linear program that we constructed here, again, we had only two decision variables and two constraints. We constructed each one of the decision variables and constraints one by one. So that wasn't too bad. When we come back in the next lecture, we're going to look at a much larger linear program with much more decision variables, with many more decision variables and many more constraints. In that case, we're going to have to create the decision variables and the constraints by using loops. So in the next lecture, we're going to do one more example on calling Gurobi from within Python, but this is going to be a larger linear programs in which we're going to create all the decision variables and all the constraints through loops. Okay, good. So this is a good point to stop.